Okay, so 15.6, page 473 in your text, we're going to talk about what happens to light rays when they travel through a medium, from air into a certain medium, and then back into air. And I just showed you in class here how light rays travel through a prism of glass. And we saw that there was some movement. The light rays seemed to shift sideways as I moved the light through the glass. So let's just read. It says, when light hits a surface, we know how to calculate if the light will refract or reflect, and to what degree. So we've done all sorts of calculations. We can use this information to tell how light will travel through any flat-faced object. And of course, what I just demonstrated for you in class, I'll just draw this up here. So we had a glass block, right? A block of glass here that had some thickness. Put it up on the whiteboard there, and I had a laser. And what happens is the laser beam kind of came in like this. What we noticed was that over here, the laser beam that exited the glass it was tough to tell, but it didn't line up with the original beam. And as a matter of fact, as I moved this, over, right, this beam seemed to shifted. It shifted over as well. And as I changed the direction, and as I started to do more of this, that beam started to change its angle as well. But what we noticed is that where this light beam would normally travel if it was just traveling through air in a straight line, we noticed that there is some distance between where that ray came out and where it should have come out. A little tough to tell with that laser that I showed you, but let's keep reading. In physics, we typically send light through prisms. A prism is a solid object that has two identical ends and all flat sides. We often use a square prism and a triangular prism. So this is a square prism. The other kind of prism that you would see would be a triangular prism. And I have one of these as well in my little lens package. But that's a triangular prism. Okay? As we continue, it says this. Now you might want to take some of these notes down that are underlined, right? So in summary, when light hits a rectangular prism, and I'll redraw this rectangular prism. You might want to take your time to do that as well. The light refracts twice. In a rectangular prism, it refracts twice. There's two separate refractions. So the laser beam comes in like this. And if I were to draw the normal here, that imaginary kind of perpendicular line to the surface, which way is this light going to bend? Towards the normal or away? This is air and this is glass here. You are right, it's going to bend towards the normal because the velocity of the light slows down, and so that's just the way it behaves. It bends towards the normal. So it's still a straight line, but at this point, it's going to bend, and I'll do my best here, red, to bend slightly towards the normal, so that this angle is greater than this angle. Everyone agree with that? Because this is pure glass, there's no other refraction that happens inside the glass. But when the light ray comes out of the glass, it's going to refract again, and this is where they're talking about, the second refraction. When we talk about light, there's the principle of reversibility. Do you remember that? Remember talking about that a little bit? It means that if light behaves one way going in one direction, it will do the exact opposite going in the exact opposite direction. So it's reversible. It can go one way, it can go the other. And so if we have a certain relationship between the angle coming into the glass and coming out, we have a similar relationship of the light that's going out of the glass. And so what happens is it's going to refract in the same manner as it went in. so that this angle and this angle are exactly the same, and this angle and this angle are exactly the same. It refracts twice. So as we continue reading, it says the light leaves the material parallel to its original path. So, a little tough to draw again, but I'll do my best here. So this ray and this ray are parallel. They're exactly the same distance apart if you were to stretch this line out. They're the same distance apart. Parallel, but shifted slightly. This is what lateral displacement is. Lateral means side to side, right? If you're talking about lateral movement, that's your side to side movement. Displacement means the change in original position. Okay, so it's a side to side change in position. But these properties hold true. It's a lateral shift and the rays are parallel if this is a rectangular prism. Alright, when light enters prisms of other shapes, we need to calculate the refraction off of each surface. So diamonds are cut so that most of the light enters the top of the diamond and reflects back out of the top of the diamond. This is what gives diamond its sparkle. So in different shapes of glass, or in this case diamond, so if we're talking about diamonds of different shapes than rectangular, okay, light is going to bend differently. Before we talk about the diamond, the typical diamond shape, let's talk about that triangular prism. Okay, so let's draw this triangular prism. And this part right here that says we need to calculate the refraction off of each surface looks like this. Let's say that we have a light ray that comes in like this. Okay, write this down. The normal is like this. So draw this triangle, draw a light ray coming in at an angle, draw the normal. So if we have air out here, and this is a glass prism, a triangular prism, then this light ray we know is going to bend away or towards the normal going into glass. Towards. So we got a large incident angle, so this is going to come in towards the normal. Okay? It's going to travel in a straight line all the way through. Now notice up here in the rectangular prism that the normals were parallel with each other. Here the normals are definitely not parallel. So that's a normal right there. It's 90 degrees to the surface. And because this angle is leaving glass into air, the angle of refraction is going to be quite a bit larger. And so you see how you get quite the bending of light here. Okay, so make sure you have this diagram written down there, the triangular prism, and then we'll talk a little bit about the diamond. Alright, if we talk about diamonds here, in this part of your notes here, diamonds are cut. Now we talk about literally cutting a diamond, diamond cutters. Diamonds are not found in the traditional diamond shape, they have to be cut. But they're cut so that most of the light that enters the diamond enters through the top. It's a big flat surface on the top. So most of the light that enters through that top reflects back out of the top. Alright, so if we look at a picture of a diamond here, this is our typical diamond shape with a flat top, and a lot of light is going to come through this flat top here. So let me just draw a red light ray as well. Okay, comes into the diamond. If this comes in perpendicular, it's going to come straight through. Now when it hits the back side, or the bottom side of the diamond, when it hits the bottom side of the diamond, remember we calculated the critical angle for the diamond? Is it big or is it small, the critical angle? It's a small critical angle. That means that any light ray that hits the surface at an angle that's greater than, do you remember what it was? 24.5-ish, I think. So that's like this angle right here. So this one, what's going to happen, this large angle of incidence is going to what? It's going to, very good, totally internally reflect. So it's going to bounce in here. It's not going to come out. This angle right here, this angle is greater than the critical angle for diamond. So what's it going to do? Totally internally reflect. And guess what? This angle now is less than 24 degrees, so it's going to come out. Actually, it's going to bend away from the normal a little bit, isn't it? So it's going to come out like this. See that? So this is why, now if you think about this, there's so many light rays that are going to come in and do this. They're going to bounce off, and they're going to come out the top. Either they're going to come out here, or the very top, or this part. And that's why there's so much light that comes out the top of the diamond that it's so sparkly. And also, at every time this refracts, so refracts a lot coming in, refracts actually a lot going out, that ray of light actually gets split a bit. And that's why you see kind of the rainbow of colors, because it actually bends so much that it starts to stretch, really, and you see all the different aspects of the light. So we got a white light ray, like this, and as it bends, it kind of starts to separate. And that's when you see the different frequencies of light. And that's why, you get the little rainbow sparkles on the ceiling and stuff with a nice big diamond ring. If it comes in at a large angle like this, okay, little bit larger than straight through the top, then here's our normal, okay, so it's going to slam on the brakes, and it's going to come down here. It's going to be closer to the normal, right? And so still down here, there's a good chance that it's going to be larger than the 24.5 degrees, and it's going to reflect and then come back out. Yeah. So anyway, so that's why diamonds are shaped the way they are, to increase sort of the sparkle. Okay? All right. Now, we've approached the end of chapter 15 here now, and what I'm going to get you to do is, before we start 16, let's just put that out here. Okay. In 15.7, so find that in your textbook there at the end of chapter 15, 15.7 on page 474. There are some applications, and you've taken notes on applications from chapter 13 and 14 already. I'm going to get you the same thing for chapter 15. Now, on that chapter 13 little quiz that we had, the applications quiz, I don't know, I think some of you can improve upon that mark.